Today I'll be deriving the volume of a cone, which is, I think, pretty easy to derive, but yeah. So let's just start defining our parameters, or important things to know. So the height, we'll just call it big H. The radius, we'll call it big R. Now, the best way to use an integral to find the volume of a cone is to split this cone here into multiple disks or cylinders. So we would, split it up into multiple circles like this. This is a perfect side view of a cone. And yeah, we'd split it up into multiple cones. We'll try to make these we'll split this cone up into multiple cylinders. And we will try to make the height of these cylinders as small as possible. So our, representation of the volume as an integral is more accurate. And let's just define this as a tiny change in h from here to here. So we're splitting this up into multiple circles here. And each circle or each cylinder will have a height of dh. And as you go up dh, you also lose some of your radius. And particularly, let's call this change in radius dr. All right? So what we're trying to represent in integral form is we're trying to sum all these cylinders up, right? So it would look something like this. An integral from 0 to r from pi r squared times dh. And pi r squared dh should look familiar to you. This is just the formula of a really tiny cylinder, or a really flat cylinder. And the integral limit from 0 to r means that we want all these cylinders within this cone have different radii. So we want to account for all those different radii. So we're taking it from 0 to r because there's always a cylinder with a radii in between 0 and r, all right? But here's the problem. We can't take an integral with two different variables within the integral. So we have to somehow get rid of this dh, and that's actually pretty easy to do. So remember what I said about a small change in dh will result in a small change of dr? Well, here's something interesting to note. So again, this would be h, and this would be big R, all right? You can see here that the ratio of dh, dr would equal h over r, because h over r is just the slope of this line, right? And wouldn't you get a similar slope if you do dh over dr? I'm not going to prove this, but it should look intuitive to you, because you can prove this by using angles and parallel lines, but that's besides the point. So it should look intuitive that dh over dr equals h over r, and then we can substitute this dh now, because dh equals h over r dr, and we plug that in here. So pi r squared h over r dr, and we take an integral. This would be 0 to r cubed over 3h r, which would equal, the r's would cancel out, so we get pi r squared over h over 3. And there you have it. That's the volume of a cone.